nuestra invitada, la doctora Nathalie T. Ella es profesora visitante de nuestro departamento de matemáticas aquí en la UAM Iztapalapa. Ella es libanesa, francesa. Ella estudió un doctorado en la Universidad de Bretaña Occidental y dos maestrías en la Universidad de Beirut y otra en la Universidad de Rennes, Francia. Sus líneas de investigación son el control óptimo, la teoría del control, los métodos indirectos computacionales, y hoy su charla para lunes de faenas matemáticas se llama El mundo de incertidumbre a través de los ojos de un matemático. Y bueno, pues muchas gracias, Nathalie. Gracias. ¿No? Otra vez no. Otra vez no. ¿Ah? Está más cerca de acá. Tal vez aquí. Que se está perdiendo. Ya está. ¿Ya? Ok. No, no sé si hacia allá, ¿todo bien? Ajá. Va. Gracias.
Okay, hola. Voy a hablar en inglés porque mi español no está muy bueno. Ok, pero voy a hablar despacio. Ok, y si no me entienden, pueden decir cómo, puedes repetir, puedes utilizar palabras en español. Okay, voy a intentar. Gracias. Okay, so I will speak today about, as we know, we have a lot of uncertainty in our world, in many problems, like in life, in our decisions, in medicine, in economy, we have a lot of uncertainty. And we will see in this presentation how we will model this uncertainty using mathematics and how to solve the problem, in the existence of uncertainty, using models of mathematics, like simple models. We will not go into complicated stuff. So, okay, now. Okay, so in this, before starting, with the plan of this talk, I will mention some words that we will be using many times in this presentation, okay, in this seminar. The first one is uncertainty. We'll speak a lot about uncertainty. So you will hear it a lot during this presentation. We will also speak about unknown parameters, because how we will represent the uncertainty, it will be through parameters which are unknown. We will also hear the word expected value, because when we have uncertain behavior of a system, we will be expecting a result which is not, we don't know what will be exactly. So we will speak about expected value, or what is called average cost, average from mediana. Huh? Promedio, okay, like promedio. So we will hear a lot the word average cost, and we will hear, okay, no, it's going, sorry. Okay, it's moving alone. no, maybe I can do it here, from here, or no, from there, eh? Because no, I should go back. It's not functioning well. Huh? Can we check, like, how to solve it again? I am sorry, but like I want to go back to the first slide. Okay, I see primer slide. No, see, más. No, it's like going, está como a moverse para enfrente. Yo quiero ir atrás.
Es que si vas atrás, se regresa.
No puedo como utilizar un computador aquí y... Ah. Sí, aquí. Sí, aquí. Sí. Okay. Gracias. Okay, so we said that we will hear words about uncertainty, words like unknown parameters to model the uncertainty. We will hear the word average cost. And we will hear also what is known by Pontryagin maximum principle. Pontryagin was a Russian mathematician, like from the 50s, like this principle. And those conditions, which we will call necessary optimality conditions, they will help us to find like the solution to the problem with uncertainty. Okay, so we will explain what are those conditions and how we will use them to find a solution to the problem. Okay? So the plan of this talk will be divided into 7 different parts. I divided it like in 7 to give more details about each part and to make it simpler on you. So in the first part, I will be speaking about, like I will give a small introduction about what is a control system and what is an optimal control problem. In the second part, I will give an example about a standard optimal control problem and how to solve it. Okay? So it will be a very easy example. In the third part, I will speak about a control system, like in the first part, but with uncertainty. As we said, we will speak a lot about uncertainty. In the fourth part, I will give you another example from like where in the part number 5, I will give the formulation of our problem on average cost. As I have said before, that we will hear a lot about average cost, because when we speak about uncertainty, we can define some average function. In the part number 6, we will speak about the main result, the most important result of this presentation, which are the conditions that we will use in order to find a solution to our problem involving uncertainty. And in the last part, I will give an example to show you how we can use those conditions, the optimality conditions, to solve the problem with uncertainty. Okay, so as I said, we will speak about what is a control system. But before of this, are you familiar with what is called Cauchy problem or no? Did you hear? Okay, so no. But it's just a terminology. Also, Cauchy was a mathematician and he defined like how to model the behavior of a system like through a differential equation that we will call like x is the state of the problem, x dot is like the speed, we can see it as the speed, and f is the dynamic of our problem. And we impose also an initial condition at the time t equals 0. And when we speak about Cauchy problem, it means that this is a dynamical system that can give us like how the system will behave, like the evolution of the system, like at each time in the future. Like if we start at time equals 0, like we can, using this, solving this differential equation, we can find how the system will behave in the future at each time. So as we said, we can predict, but we cannot modify the evolution of the system in Cauchy problem. When we speak about control system, we will add an extra function, which we will call u. And this function is what we call control. Okay, the function u is the... Okay, so the function u is the control. And using this extra function that we include in our system, we can modify the behavior of the trajectory. Okay, so this is like a function that we add and we can manage. So the system can be, its evolution can be affected. So it's different than the first problem where we can only predict, but we cannot modify the behavior of the trajectory. In the control system, we can add an extra function, and this function can modify the evolution of our system. And if we add to this control system what we call a cost, like an extra function, we will start speaking about an optimal control problem. Okay, so we have a control system modeled by this dynamic. If we add a cost function, like a function either to maximize or to minimize, like imagine you are driving a car, for example, and you want to reach some destination, like with the minimal possible time, like the fastest to your destination. So the cost in this case is the time, and our job is to minimize the time. So what is the strategy, the control strategy, to reach our destination with the minimal time? Like, for example, it can be by some speed limit or by going to a certain street, like where there's no traffic or something like this. So in this case, we have an optimal control problem. So speaking about optimal control, as we said, we will hear also this terminology. So what is an optimal control problem? As we said, we have a lot of problems in real life where we have models of optimal control problems, and a standard one is to minimize some function. Here I take like the integral between 0, 1 of some function g, depending on time t, on the state of our problem x, and on some control u. So in this presentation, always x is the state, like the trajectory, and u is the control. And in this optimal control problem, we aim to minimize this integral function, taking into account the behavior of our system. And how this behavior is modeled is through this dynamical equation x dot equal f. And we impose some initial condition and final condition on the initial time t equals 0 and on the final time t equal 1. Okay, we are working in the time interval 0, 1. And we consider the function f and g like differentiable, so we can compute the derivative of them. And what is the goal, the objective of this problem is to find what is the best control strategy, what is the best strategy that can minimize this cost function. As I have said before, like in the example of driving a car, we want to reach a destination with the minimal time, starting from here, reaching there. What is the best way to go from here to there? By minimizing time. So this is what we call by control strategy, how we will control our system to have kind of minimization of some cost, depending on fuel consumption, on time, on distance. We can have it like in different ways. Okay, so how to define this control strategy? The first thing to do is to define a function that we call usually Hamiltonian. And this function, which we call capital H, will be like the scalar product between an arc P and the function f. I remind you that function f was the function in the dynamics, okay? Plus the g. G was the integrand in the cost, like we had, like minimizing the integral of some function g. So we include this function in this term, okay? So we have p scalar f plus g. F is the dynamic and g is the cost, the integrand of the cost. So once we define this function, which will help us to define what the control strategy, we can start like establishing what is the Pontryagin maximum principle. I remind you that that was the first slide of this presentation. I told you we'll hear also a lot about what is a Pontryagin maximum principle, who was like a Russian mathematician. And he invented this maximum principle to help us to define a control strategy to our problem. So what is maximum principle of Pontryagin is about? So we consider a solution. We assume that there's a solution to our problem. And this principle assumes that there exists an arc P such that we have some conditions that should be satisfied. So the first one is that the derivative of this arc P is equal to the, are you familiar with partial differential? Or not? Like, because since H depends on several variables, X and U, so we can define like the derivative with respect to X, the derivative with respect to U, the derivative with respect to T. Okay, so we don't have only one derivative, we have several. So the first equation, which we call adjoint system, defines the derivative of this arc P as the partial derivative of this function H with respect to X. So we derive this, we have the derivative of this sum with respect to X, which gives us P gradient of F with respect to X. Here there's it's a plus, okay? Plus gradient of G with respect to X. The second condition, it defines the behavior of this arc P at the final time, t equal 1. Okay, we are working in 0, 1, the time interval 0, 1. And it's called transversality condition. Like the names are not so important for now. And the third condition, it's what is called maximization condition. And it says that if we derive H with respect to the control, U, okay, I remind U is the control, X is the trajectory. And we replace it by the optimal control, like by the minimizer here. So this derivative is equal to 0, okay? So those conditions, they will help us to define the control strategy. What do we mean by this? So as we said, we have a problem of minimizing some cost. We have a dynamical system. And the idea is using those conditions, if we solve condition 1, 2, 3, it will give us a set like this red set containing all the solution of the problem. So if we solve those equations, we will end up finding an extra information about where the solution of the problem exists. Okay, so it will give us information on all the points in red here, and those points will contain the set of the solution to the problem. So this is the idea of the Pontryagin maximum principle, is to define conditions that we will solve, and after solving them, we will have an information about the solution of our problem. So now let's give an example how to apply those conditions in a standard optimal control problem. Okay, so we consider the problem of minimizing the integral of u squared. Okay, a simple function. We have the dynamics of the problem, x dot equal x plus u, and we impose an initial position on the problem, but without a final position. So x at the final time is free. So here, if we look to this problem, what could be the minimal value of this integral? Like what value of u can we see like directly in a very simple way that will be like the minimum? It's for u equals 0, okay? For u equals 0, this would be the minimum value that this integral can take, because we have u squared, so always it's positive. Okay, so we expect that the optimal control is 0. So if we replace u by 0, all this term is 0, and this could be the minimum. So we will verify this using the conditions that we presented in the previous slide, the Pontryagin maximum, the maximum principle, okay? So those conditions, if we solve them, we will see that it's true that the solution to this problem is u equals 0. Okay, so as we said, we first defined a function which we called the Hamiltonian, and we said that this function consists of h equal u squared. U squared is the cost, plus some arc p, some function, time the dynamics. The dynamics in our example is x plus u. Once we define this Hamiltonian, okay, so we can apply the conditions of our theorem, the Pontryagin maximum principle. The first one is the maximization condition, which we mentioned before, and we said that if we derive h with respect to u, this quantity should be equal to 0, okay? So if we derive it, we have the derivative of this with respect to u is 2u plus p, this amount equal to 0. And we substitute u by the optimal solution that we assume that it exists. And we have that u bar equal minus p over 2. The second condition is the adjoint equation, and it said that the minus p, the derivative of p, is equal to the derivative of h with respect to x. And if we derive this quantity with respect to x, it will give us p. So we have minus p dot equal p. This is an ordinary differential equation, and its solution, it's easy, and it's the exponential, okay? The solution of minus p dot equal p is p equals c, some constant, time exponential minus t. And the last condition, it gives us an information on the arc p at the final time t equal 0, and it is equal to 0, okay? Okay, so if P1 equals 0, we substitute here, so CE minus 1 equals 0, and this will give us C equals 0. So we know already that this constant C is equal 0. We substitute here, and we arrive to the fact that P is equal 0. Okay, so P equals 0, and we substitute here, so U bar is equal 0. So those conditions, they confirm that our optimal solution is u bar equals 0 as our intuition, because in the beginning we said we have the intuition that the solution to the problem is u equals 0. So using those conditions, maximization, adjoint equation, and the transversality, we confirm that the solution is true, like the solution is u equals 0. So this is the reason why the maximum principle exists. It is to help us to confirm our intuition about the solution of the problem. Okay. Okay, one more. Okay, so now we spoke already about control systems, about optimal control, like minimizing some cost function. Now we will speak about control system with uncertainty, like how we can model the uncertainty in a problem. So if we remember before, when we spoke about control system, we had x dot equal f t x u, but there was no uncertainty before. So now, to model the uncertainty, we will add some unknown parameter, okay, omega, in the state and in the function f in the dynamics. Okay, so here the uncertainties are taken into account via the omega, okay? And we will define an optimal control problem. Like before, we defined a minimization of some cost function. Here, what could be the cost function in the case of uncertainty? So what we will speak about is a trade-off. Trade-off, it's like compromiso, okay? We have uncertainty and we will see all our uncertainties and we will find the best way to choose between all our uncertainties. And this is what we call like trade-off, or like compromise, okay? And to define the optimal problem, we will define a cost function, which we will call average, okay? Like we already said, when we speak about uncertainty, we speak about unknown parameters, and the cost function to minimize or to maximize will be called, what we will choose like to define, it will be called cost function. I will mention after how it will, which form it will take, this cost function. And for this problem, we will also define the maximum principle, the corresponding maximum principle, which will give us condition. And if we solve those conditions, we will end up finding our optimal solution or an information about the optimal solution. Okay. Okay, so now before speaking about the average cost problem, which will be the main topic of this presentation also, we'll speak about previous works in the literature where also uncertainty was taken into account. And those problems are like called minimax problem. So it's like minimizing the maximum of some function. And this function has uncertainty via the unknown parameter omega. Okay, so in this type of problems, the idea, okay, let's give a small example to understand what is an example of minimax problem. I think that we all know the game rock, paper, scissors. I don't know how it is in Spanish, if it's the same. Yeah, okay. So this is an example of uncertainty, okay? Why? Because what is the uncertainty? If we are two players, okay, the other player will choose about a set of uncertainty, which will be or rock, or paper, or scissors. So we have omega. Omega can take three values, rock, paper, or scissors. So once the other player will decide, I don't know yet what he will decide, I will try to guess what he will, like to predict what he will choose. And according to this, I don't want him to win this game. So I want to minimize his chance of winning the game. Okay, so this is the idea because I want to minimize, like to reduce the chance of the other player of winning. Okay, this is the idea of Minimax problem. So we have two players, each one working against the other. One wants to win and let the other lose, and vice versa. Okay? So this is an idea of Minimax problem where we have uncertainty. So now let's go to example of real life problem where also uncertainty can appear. So if we take an example from aerospace engineering, so imagine that we have a spacecraft which is collecting images, okay, in two different times. So let's say that at time t equals 0, it collects one image. On t equal 1, time equal 1, it collects another image. And the idea is to minimize this time between two collection of image. And this system, in fact, it includes a lot of uncertainty. The uncertainty is in the behavior of this, what is called gimbal. Even me, I am not so familiar with those terminology, but we can see that this, it's called like gimbal or gyros. Okay, so it's like doing this behavior, okay, while taking images, and its behavior has a lot of uncertainty. So the uncertainty appears in the behavior of this circle, okay, disk. Okay, also we will not focus too much on the dynamics of the system because it's a difficult system, but we will focus on the fact that this rotation that we said of the gimbal, which has uncertainty, is modeled through this simple, more or less, ordinary differential equation through this uncertain term, mu, okay? Which is the control, which is some extra control modeling the behavior of this movement of the gimbal and the spacecraft. And as we said, the idea is to minimize the time between two collection of image. Okay. So in this paper, which I mentioned here in 2015, it was published by 3 engineers, in fact. They studied like situations of this problem. So if they consider all the values of the uncertainties, okay, so we have unknown parameters. If they consider all of them and they take it equal, like they take the average of them, the mean value, okay, of all those different values of the behavior, they end up in a system which is not controllable. Like it will not give it didn't give them any type of information about the best strategy to use in this problem. But if they consider every uncertainty, like they take into account every uncertainty, and they consider it also in the cost, okay, through the integral, like they take all the behavior of the system for each unknown parameter, and after they take like the average of them, and they solve the problem, and they found that this is a better strategy to do, other than taking only one unknown parameter and forgetting about all the others. So the idea is to take all of them and to take the average of them. And that's in this way, like we have like satisfactory results. Like the problem, it will be controllable and we can get information about the behavior of our trajectory. So this is an example from a real life problem about average cost, okay? Okay, now we will introduce like in a theoretical way, because before we said aerospace engineering, the example. Now we will give like more general example, not only from aerospace engineering, where we have uncertainty and we have the average cost problem. So we will use this notation of omega for the set of the uncertainty. Okay, we collect all the uncertainty in one set, which we will call big omega. And we will consider on this set like a probability measure. Okay, a probability. So what is the probability of choosing this uncertainty? What is the probability? Like each uncertainty has some probability. And we will call it mu, okay? With this sign mu. So the problem will be minimizing the integral over all the, like we said before, like we take all the uncertainty, all the behavior of our trajectory for each uncertainty, and we take some function g, like its integral over all the possible uncertainties. That's why like we call it average cost, okay? And we minimize this problem subject to dynamics. The dynamics also depends on the uncertainty, and we have some initial condition, okay? We don't care much to put also uncertainty on the initial condition. So uncertainties are taken into account. And what is the goal of this problem is to find the control strategy, as we said in the beginning. When there was no uncertainty, the idea of maximum Pontryagin maximum principle was to find the best control strategy. Here is the same. We are interested in finding what is the best control strategy for this problem. Okay. One more. Okay. So if we compare this problem to the rock, paper, scissors problem, okay, the Minimax problem, we can find that we have this measure, the probability on the set of the uncertainty, while in the other problem, it wasn't given. Like here, we assume that this probability measure is defined as like it's already defined. In the other problem, rock, paper, scissors, for example, it's not defined. Okay, and the difference also with respect to the rock, paper, scissors is that here we minimize an average, while in the rock, paper, scissors, we were minimizing the maximum. Like, because we said we want to minimize the chance of the other of winning, like the maximum probability of the other of winning. So it's a different framework of problem. So what is the important theorem of this average cost problem is to define the Pontryagin maximum principle, or the necessary automatic conditions, which is a set of conditions, as we have said before, like in this, if you remember the three circles, one inside the other, those conditions will give us an information about where the optimal solution, where the solution of the problem exists, okay? So the first condition, we assume that the solution of the problem, we call it u bar x bar. So there exists a function p, I use the same notation, p, such that the first condition is the maximization condition. Okay, the second condition is, it gives, like, it's more or less the same as before, but here we should take into account the uncertainty. So the main difference is, like in the first equation, before it was P scalar F, F is the dynamic, is equal to the maximum of P scalar F over the set of controls. Here, when we have uncertainty, to take into account all the behaviors of the trajectory, we should take the integral, like to find the average. Okay, so every uncertainty is taken into account. That's why, like, the difference with respect to the standard optimal control problem is the fact that we consider in the maximization condition, the integral over all the uncertainties and all the behavior of the trajectory for the different unknown parameters. So the second one, it's more or less the same as the previous one, except that we have the dependence on omega. And the last condition is also like the standard optimal control problem, but we have also dependence on the unknown, on the uncertainty, omega, okay? So those are the three conditions which are adaptation of the standard case to the formulation when we have uncertainty. So now we will see how also to use those conditions to have an information about the set where the solution of the system exists when there's uncertainty, okay? So the idea is to solve those three equations and we get the, like this information that we are searching. Okay, so the example, how to use those conditions. Okay, so we consider also a simple example. We want to minimize the integral over the set -1, 1. So all the uncertainties are on this like interval from -1 to 1, okay? We are in the real space of this function minus the absolute value of the state at the final time minus omega. Omega is the uncertainty, okay? And we consider a probability, which is d omega over 2. So in this case, if we forget about this term, it will be like the measure. Are you familiar with Lebesgue measure? Maybe not. Lebesgue. No? Like it's a measurement of, if you have a line -1, 1, its measure is 2. Is 1 minus -1, okay? So here is the same. It's like we measured this interval and we divide it by 2, okay? And we have a simple dynamic, x dot equal u. U is the control, x is the trajectory, and we have an initial condition. Okay, so for this problem, we have a solution, which is x equal t, u equal 1. The set of uncertainty is -1, 1, which is here, this one. The probability, as we said, is like the size of our interval, and we divide it by 2. Okay, it's d. We put it as d omega over 2. We have our dynamic f equal u, which is this term, and the cost function, like what is under this integral, is this, minus the absolute value of x minus omega at the final time 1, t equal 1. So now we will solve the conditions in the previous slides. Okay, so what we will use for the conditions, as we have seen, we will use the derivative of x, of f with respect to x. So the derivative of u with respect to x, it's equal to 0. And we will derive also this absolute value. So the absolute value, it's not differentiable. Like you cannot find directly its derivative. It's not like derivative of x equal 1, derivative of x square equal to x. So here it's a type of generalization of the notion of derivative. So the derivative of this quantity is pair, which is -1 and 1. So those quantities will be used in order to solve the conditions of the maximum Montriagin maximum principle for our problem. So we apply this maximum principle and we get that P dot, I remind you that P dot was equal gradient time P. And since the gradient is 0, so P dot is equal 0. Then P is constant, but we didn't solve it yet because we need to know what is this constant, okay? From the second condition, which we call transversality condition, it's not important, like as I said, the names, we can find that P is equal to the gradient of this quantity, which is or -1 or +1. So Now we will try to find out which is the correct answer. Is it the 1 or -1? So we still have one condition which we didn't use, which was the maximization condition. So we use, and we did the first case. If we consider that P is equal -1, by solving the maximization condition, we finally arrive to the fact that -1 is equal +1. So the case of P equal -1, it's not valid, okay? It's not correct. So now let's check if P equal 1 is the correct answer. So using also the maximization condition. So now, if P equal +1, then using the maximization condition, we arrive to the fact that 1 is equal, like maximizing this quantity over -1, 1. We arrive to the fact that 1 equal +1, which is correct. So those conditions will give us the true fact that this quantity is equal 1 and not -1. Okay, for this minimizer. Okay, so now to conclude, what we saw in this seminar is that what is a control system, what is an optimal control, what is a control system with uncertainty. We saw also the Pontryagin maximum principle for a standard optimal control problem and for average cost problem. We saw the difference, how to behave when there's no uncertainty, which is a simpler case, and how to behave when we have uncertainty, like via what we call by Pontryagin maximum principle. What we have also seen, we've seen like how to use, like we gave two examples, one in the absence of uncertainty, one in the presence of uncertainty, how to use the conditions given by this maximum principle to solve our problem. And for the future, like we can extend the problem formulation to put more conditions on the problem. Like it's not so important for now, but like put extra condition on the problem to see, like to complicate it more and to give also more information about the optimal solution. Because if you remember those three circles, the red one was containing the solutions. So how to maybe reduce this red circle so we have more information about where the solution exists. Okay, so that was everything. I hope that it was a bit clear, or I don't know, but I am ready for any question. Thank you. Gracias.
Muchas gracias, Nathalie. ¿Alguien tiene alguna pregunta? Aquí. Allá, Alejandro.
Thanks with the talking with me. My question is, in this tool mathematic can be used to electronic processing to analogic to digital, have errors in this process, the stochastic signal for the noise. This tool can be used to this. Well, no, this have an error with the value of the level of voltage can use in the processing of the signal.
Signal processing.
Because
I mean, if you are speaking about stochastic, this cannot be used in stochastic, because in stochastic you don't know the set of uncertainty. Here you know what is your set of uncertainty, okay, you know what it is, and you have like the values of each unknown parameter and the behavior of your trajectory for each uncertainty. So it's deterministic. So stochastic cannot be applied here. This is a deterministic problem because you know the behavior, you know the set of uncertainty and the behavior of each trajectory, like the solution for each unknown parameter, for each uncertainty. So in signal, because I didn't get well your question, but if you want to apply it in stochastic, you cannot. This technique, it's only for deterministic. Okay.
Una otra pregunta. Tenemos una pregunta aquí en YouTube que tal vez puedan proyectar aquí en el chat.
Jorge.
No sé puede quitar ahora. Es what is called transversality condition. And it is has to do with some kind of orthogonality. Maybe for the first slides.
Yes, I mean it's Jorge. He can hear me. Jorge?
Yes.
Okay. The transversality condition, it's the same as the boundary condition. Yeah, I mean it's the same as boundary condition. I can hear him or no? I can.
Yes. We are broadcasting this.
Yeah.
And the second, it has to do with some kind of
yeah.
Pues okay. Muchas gracias a Nathalie.
Gracias a ustedes. Ay.
Nos encontramos este día para la sesión sobre matemáticas, playa y no sé más, de Puerto Vallarta. Vamos a tener esta charla en 15 días y bueno, pues nos vemos, vamos por la clase Ignacio, por estar acá, nos vemos. Muchas gracias.
Fue complicado para ellos.
No, pero bueno, seguramente, pues en general son cosas complicadas, pero yo creo que es un poco aunque efectivamente pues está esta como estás hablando del sector, a lo mejor hay probabilidad de hacerlo.